a gas from one volume to another and keep its temperature constant. Huh? Isothermal? And because it has to be reversible, a reversible path, then we can use a reversible path. So an isothermal reversible path. We can find an isothermal reversible path that will take us from this state to this state. And if we integrate dq reversible over t along that path, we're going to get the value for delta S. So let's write this out. So, because it's reversible, we swap in our ideal gas pressure, or our ideal gas version for the work. So we take in nRT over V. There's another factor of T down here because it's isothermal, the two T's are the same. And so those guys will cancel. And we're left to integrate nR times the, we're integrating 1 over VdV, but nR outside of it. And so our answer ends up being nR natural log of V final over V initial. What is the value of V final over V initial for double the volume? NR line 2, right? So using the differential form, not using the statistical form, using the differential form, we end up with the same answer that you get when you plug in S is equal to KD log ways and figure out exactly how many different arrangements can be made that yield the same result. Okay? You'll notice that NR line 2 is positive. It was observed that processes that happen spontaneously result in an increase in the value of the entropy of an isolated system. In this case, we're looking at isolated systems, so we're only looking at entropy changes in the system. We're not looking at the surroundings. For isolated systems, a process that happens spontaneously will necessitate a increase in the entropy state function. And so the suggestion is that processes that generate more disorder in general, more disorder in the universe, are the ones that happen spontaneously. Let's look again. Let's look back at that temperature equilibration problem. This one I'm going to let you guys work on together on your own or in group or whatever. You have that say this is 2 blocks of iron. It has iron T capacity. And this guy starts off at T hot. This guy starts off at T cold. Let's just define these. Let's say this guy is at 100 degrees Celsius, and this guy is at 50 degrees Celsius. What's going to happen is that heat is going to flow from one side to the other. How do you describe the heat that flows out of a piece of material at constant pressure? Q of constant pressure is equal to the integral of Cp dt, right? You might, that is one of the things that we mentioned when we were talking about enthalpy changes. And so you can quantify the amount of heat transferred by using this equation, integral of Cp dt. And you know that the process of heat exchange is going to stop once the two temperatures are equal. And so you'll reach some identical final temperature in these guys. What I want you to do now, remember, ds is the integral of dq reversible over t. T is not constant in this case. The t, as this block loses energy, its t decreases. As this block gains energy, its t increases. And so t can't come out of the integral in this case, so it has to be factored under the integral. It has to be integrated with it. Do me a favor and get me expressions for the change in entropy of each individual subsection of the block. Call this delta S1, call that delta S2, and tell me what is the final temperature and what is the total entropy of the system if the system is complained of, or is composed of block 1 and block 2. Put your tables and groups, get together, and start talking about it. What's that? Oh, assume that the masses are exactly equal. So the mass of this block and the mass of that block are identical.
You gonna turn that off?
Yeah, you can turn it off.
How do you turn it off?
It's just a little button.
Oh, you mean right
I'll
here?
just grab it.